Pedigrees are used to study generations of individuals. They're oftentimes used for humans because every new generation for a human family takes a number of years, like 20 to 30 years. And so instead of looking forward, lots of times scientists who are tracking a disease or disorder will look backwards. And so a pedigree allows us to basically see a family tree genetically. In a pedigree, anytime you see a square, that represents a male. So here we can see individual number 2 of generation 1 is a male. Anytime you see a circle represents a female. If the individual is affected with the disease or disorder we're tracking, then it will be shaded in. Here we can see that this couple had a daughter, a son, a daughter, and a son. In that order in their generation 2. Their daughter never got married. Their son did, however, get married, and that is his spouse. That then led to generation 3, and individuals 2 and 3 of generation 2 had 3 children, a girl, a boy, and a girl. And so that's what a pedigree represents. Anytime that you see a bracket, that represents twins. I know it says fraternal, but it's just twins in general. And anytime you see a cross underneath their symbol, that means that that child was miscarried. So let's look at our very first disease, and it's going to be deaf mutism, people who suffer from hearing loss and a lack of being able to communicate verbally. That gene is an autosomal recessive disorder. So most people don't have it. If you have it, it is a recessive disease, and so that allows us to be able to then track it. So here what I'm looking at in this particular pedigree, I'm going to go ahead and fill in everybody that I know that is affected. And anybody that I know is affected is going to have a recessive genotype. So all of these individuals will be little n. And I know this is a recessive disorder because the children of 2 affected people are also all affected. Those are supposed to be N's. I know they look terrible. There's an N. These people are all affected. Just like so. All right. So that means now that we have to assign the alleles for the people that are unaffected. And we can do that by looking at their offspring. So I know that these people are unaffected, so I know they're at least one big N, but they did have a child that has the disease, so they have to be carriers. So sometimes we will shade them in like so to show that they're normal, but they have to be heterozygous because otherwise they could not have made that child there. And so that child got both recessive alleles from mom and dad. And so if I look at this child, normal, so is her husband, but they had a child with it, so they're heterozygotes. This person has not married, has no offspring. Therefore, we don't know what their other allele is except to know, let me go shade these carriers. The only thing we know about individual 3 and generation 2 is the fact that they're normal, but we don't know what the other allele is, so we have to leave it open because you don't know if they are homozygous dominant or if they're a heterozygote. You just know they're normal. Again, normal appearing parents to the generation 3, but they had a son with the disease, so that makes them carriers. And then if I look at this individual, this was a daughter. She's normal appearing, but doesn't have anybody else in her following her in generation 3, so therefore we have to leave her blank. So you could just continue to work through that puzzle and that punnet. In this next punnet, we can see we're talking about a sex-linked, X-linked trait, which is hemophilia. It is also a recessive disease. So in order to have the disease, you have to have, if you're a girl, both small alleles, or if you're a boy, you have to have at least just one. Remember, sex-linked, X-linked traits affect boys and girls differently. So if you are a girl, you have to have both recessive alleles. If you're a boy, you only need one. So here what we can do is begin to assign alleles to individuals we know for sure. So this is a boy that is colorblind. Here's another boy that is colorblind. When you look at a pedigree and the majority of the people affected are boys, then that is a X-linked, sex-linked trait. And so far, the only living people to have this disease are boys. Here, these girls got a double dose from their parents, but that was lethal, and they were miscarried. Same thing for this girl. So if I want to go back and track these parents, I have to keep up with their X's. I have to keep up with their Y's. I can see here that this boy received a Y from dad because mom can't give it. And so I know mom then has to be at least a carrier because she gave that little allele to her son. And so we can shade her in. Dad is normal, so we know for a fact he has to be a big N. Again, this is an X-linked, sex-linked trait, so don't put anything on the Y. This person married a woman who looks normal, but they had a daughter that was miscarried, so she has to be a carrier. She has to. This individual is a girl, and she appears normal, and we don't know anything else about her at this time because she has no offspring, so we're going to leave that blank. And so you could just go on and fill in the rest of that pedigree, not a punnet, a pedigree, sorry. All right, this last one is super unique. It is a dominant disease. And so in order to be normal, so brachydactyly, these are people with unusually short fingers. To be normal, you have to be little a. And so I know that I'm normal. And so did that wrong. Back up, Miss Keene. Everybody that is not affected has to be little a. So this just isn't a very common allele that's found in the gene pool. This person has the disease, so they have to have at least one big A. But look, they had a son that was part of twins that is little a, so he's got to be heterozygote. This individual is big A, little a, because they have the disease, so they have to have the dominant allele. And then dad can only give a little allele, so that is a heterozygote. This individual also has the disease, and then dad could only give the little one, so that is a heterozygote as well. How do I know this is a dominant disease? I know this is a dominant disease because these two parents have it. If it were recessive, all their children would have to have it. And so I know they're heterozygotes because they made a kid that doesn't have the disease. And I know this is a dominant disease because you cannot have a child that's normal from two affected people if it is a recessive disease. Everybody would have to be affected if it was recessive, just like up here. So that's how I know this is recessive. And this one tells me that it is a dominant disease because that child is unaffected. And then this one, if I look at all their survivors on the pedigree, they're boys. So I know that's sex-linked. Okay.